extends out that direction, I'm going to have to go with group 2 and hope that doesn't happen.
So is that a three-dimensional graph?
It's not three-dimension means that it's got 3 dimensions.
Yeah.
We tend to draw it like that. So that, but no, that's not three-dimensional.
So,
it's just splitting up the two-dimensional region.
so why is it splitting it up in 4? So what is the middle line, the straight line in the middle representing?
Overall, probably an overall mean. Because it's right down the middle.
Or is it just the 0 line?
Yeah, it's. So do I need that line at all? I don't need that line at all.
Yeah, I thought it was like.
That's the line that separates group 2 and group 3.
That's the line.
If you go
Yes,
back,
just by one-way ANOVA type.
yeah.
gain.
So if you go back a slide, it shows you the lines that these bisectors come from.
Oh,
So it's
so
the
it's
perpendicular
the
line to that
perpendicular
top line.
bisector.
Yeah.
There's nothing like geometry. Remember geometry class? You guys had geometry. There's no logical reason why geometry is a required subject in school. They like to give children an exposure to mathematics that different. Yeah. Anyway. It's a different argument about the education system. So we're going to have the perpendicular bisector here, 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 and it becomes, there's a geometric argument. And by the way, how do we prove all these things? Mathematically, we use a bunch of geometry and a bunch of linear algebra, so it becomes fun. Ah, see, I should just go forward in my slides. You guys can do that, right? You can barely see the lines here. But I got my classification right. No, I didn't, because I said go this way and classify that point as group 2. And I was wrong. So that again, you end up splitting up the space into classification. So these lines are optimal in some sense, but who's to say they should be lines? Maybe they should be curves. And we don't have to use linear methods to classify. One of the problems is if you don't use linear methods, then it becomes even more confusing what you're going to do, and the lines work better in papers, I can tell you that. Getting reviewers to understand what you're doing. Using distance to classify, that's sort of, okay, maybe we should. Let's see. We know that it's closer to the mean. So yes, classifying to the closest mean is Euclidean distance, right? Using Mahalanobis distance is different. But if you standardize the data, they're basically the same. So typically, if you want to make it fair, you standardize the data. That doesn't necessarily mean that'll give you the best classification. It's not necessarily true that all the variables are equally important. And as soon as you standardize them, which is what we do almost all the time with principal components, with partial least squares, with discriminant analysis, not with logistic regression typically. I don't think I've ever seen a logistic regression where they said, oh, we'll standardize the variables first. It's not necessary, and it's not common. Why is it not common? Because it isn't necessary. Remember, logistic regression doesn't have any optimality properties. It just works well lots of the time. For standardized variables, the Euclidean distance and the Mahalanobis distance are the same. We end up with a good plot. If you have two groups, you get the same answer using the Mahalanobis distance way and the canonical correlations way. You do get different answers using the Fisher's way and the Mahalanobis way if you have more than two groups. So you could try them and see. For better or worse, the Fisher's way doesn't happen very often. Okay, so these are notes that are sort of like this now. The linear part of it. Here's the line that differentiates between those two groups. But the groups, if it's a point cloud, then having a line isn't necessarily a good idea. Do you have the other picture? Here. In this case, some of the slides, by the way, used to be they used to have yellow all over the place. Now the yellow's hard to see. But so this is an example, and I drew one of these on the board on Tuesday, maybe? I don't know, sometime in the past. And when this sort of thing happens, when the point clouds look like this, then they're points that aren't, it's not clear that you're classifying them correctly based on the line. Well, putting a line through here is not necessarily, so what's the point that gets misclassified by a line? It's one that's here. So a point that's right there, where's my cursor? A point that's in between here, that point cannot be from group 1. Virtually impossible. Group 1 has little variance in this direction. This point right here is really far from group 1. If you use a linear method, then that may not get it right. Because the linear method is going to assume that the variability is the same in these two groups, and it's going to force them to look the same, even though they're not. And so if your data looks like this, and you go, oh, I need a quadratic method. This point right here is almost guaranteed to be from group 2. Because group 2's got a lot of variance in this direction. So that point is going to get misclassified by linear methods. You need quadratic methods to do the game. Okay, let's see, where's the... This is whether the covariance, so if the covariance matrices are different, and how should you think about that? You should look at your data and say, oh, am I in this situation? Do they look sort of similar? Well, let's go back to our point clouds. Back here. I probably need some more resolution to tell. But this one sort of looks like it's a point cloud, like a little bit like that. This one is a little bit the other direction. If I wasn't doing beautifully with my linear method, I could go to a quadratic method. But I don't need to, because I'm getting really beautiful results with the the linear method. But in reality, you're not going to have a pretty example. You're going to be in some situation where you're more likely to be see, in this case, if your point clouds look like this, life is good. They look the same. So you're happy, or not too different from each other. And your point clouds look like this, those are clearly not the same. And you're going to get worse classification using a linear method because you're going to force them to look the same when they don't look the same. So don't force assumptions on that aren't true. The same thing's true with variances. You assume that variances are equal. When I initially do my one-way ANOVA for the 90 variables that I have on the fuel, I'm going to assume that the variances are the same, but then I look at the darn plot and see if my assumption makes sense. You need to evaluate whether your assumptions make sense. I've ranted on this before, but just to remind you, equal covariances is like assuming equal variances. You do need to check, but your visual check is 100 times better than the mathematical check. Testing covariance matrices is doable, and I'll show you examples of where it's done, but it's even worse than testing whether